This problem is yard block housekeeping, the continuous, systematic reorganization of yard stacks so the terminal does not drift into chaos. The goal is to prevent cascaded rehandles, where one small access mistake turns into many extra moves. Think of housekeeping as preventive maintenance for container flow. You are not moving containers for a customer right now. You're moving them to keep the yard accessible, balanced, and resilient against tomorrow's workload. In the scenario, Terminal Delta's main yard has 48 blocks arranged in a 6x8 grid. Each block holds 120 containers in a 4x6x5 configuration. About 800 containers arrive daily while 750 depart. That constant imbalance creates pressure. Without planned housekeeping, some blocks overload, access worsens, and emergency retrievals trigger a domino effect. Poor stacking decisions can trigger a container avalanche effect. A small access mistake can cascade into dozens of extra moves. Housekeeping decides which containers to relocate, when to perform those moves, and how to sequence them to minimize disruption. The operational challenge is doing this while normal vessel, gate, and equipment work continues. This deck is organized into tiers. Tier 1 is a minimum cost flow formulation on a time-expanded network. Tier 2 is a weighted priority dispatch heuristic. Tier 3 uses ANT colony optimization for move sequences. Tier 4 uses deep reinforcement learning with a deep queue network. Tier 5 uses an integrated digital twin, and Tier 7 emphasizes human and artificial intelligence collaboration with explainable output. Tier 1 models container moves across blocks over time as a minimum cost flow. Movement arcs represent relocating containers and carry relocation cost. Staying arcs represent keeping containers in place and carry holding cost. The model enforces flow conservation and capacity limits per block and period. Operationally, that means every move is accounted for and no block is allowed to exceed its safe working capacity. The sets define the objects in the model: yard blocks, time periods in the planning horizon, and container states such as ideal, suboptimal, and critical. Operationally, these states represent how healthy a stack configuration is. Containers in a critical state are likely to cause future blockage or emergency rehandles, so the model needs a way to track and price that risk. Parameters include the cost to move containers between blocks over time, capacity of each block over time, demand for space in each block over time, and holding costs associated with container states. Operationally, these parameters represent both the yard's physical limits and its economic signals. Move costs consume crane time and transport resources, while holding costs represent the future pain of leaving containers in bad configurations. Decision variables represent how many containers are moved from block I to block J at time t, and how many containers are in each state at each block in time. Operationally, this lets the model represent both actions and consequences. You track moves explicitly, and you also track whether the yard remains in good or deteriorating condition. The objective combines movement cost and holding cost across blocks, states, and time. Operationally, you can think of it as paying for two kinds of waste: the immediate cost of relocating containers and the future cost of leaving the yard in a risky, hard-to-access state. Flow conservation ensures that for each block and time period, the number of containers flowing in and flowing out is consistent with how many containers are present and what the block demand is. Operationally, this prevents magic solutions where containers disappear or appear. Every container movement must be accounted for, and the block's space usage must remain consistent. Capacity constraints ensure the total number of containers in a block does not exceed that block's capacity in each time period. Operationally, this prevents overload. Overloaded blocks create congestion and force reactive relocations that disrupt vessel and gate operations. State transition constraints connect moves to container state evolution. If containers remain in place or are not relocated, their state can remain suboptimal or critical. Operationally, this captures deterioration. When housekeeping is delayed, access problems grow, and the future workload becomes more expensive to serve. Non-negativity ensures the model does not allow negative flows or negative container counts. Operationally, it is a basic feasibility rule. You cannot move negative containers, and you cannot have negative inventory. This slide shows the network flow representation of yard block housekeeping. Operationally, the diagram helps you see the structure: time-expanded nodes, movement arcs with costs, and holding arcs that represent keeping containers in place. This is why the model can jointly decide when and where to move containers. The 4-block example uses a 3-hour horizon. Block 1 starts at 120 TEU with demand minus 20 at time 1. Block 2 is 80 TEU with demand plus 15. Block 3 is 95 TEU with demand plus 10. Block 4 is 110 TEU with demand plus 25. The optimal plan moves 20 containers from Block 1 to Block 2 at unit cost 15, for a total movement cost of 300. Operationally, that one decision relieves an overloaded block and provides space where demand is increasing. Tier 2 scores candidate moves by urgency, accessibility, efficiency, and cost. It executes the top scoring move if the score exceeds a threshold. Operationally, this supports real-time housekeeping under changing arrivals and retrievals. Instead of solving a large flow model every time, you make a fast decision based on a composite priority score. This slide focuses on the priority score. Operationally, the score is where you encode terminal policy. If urgency is overweighted, you may churn the yard with too many reactive moves. If cost is overweighted, you may avoid necessary moves and let the yard degrade. This slide shows the weighted priority dispatch algorithm flow. Operationally, the flow is generate candidate moves, compute scores, choose the best move, execute it if it passes the threshold, then update the yard state and repeat. This is the first pseudocode segment for the heuristic. Operationally, focus on how candidate moves are generated and how each score component is computed, because these steps determine whether the heuristic reflects real yard priorities. This segment continues the pseudocode. Operationally, the key is the update step. After each move, you must update utilization, accessibility signals, and urgency indicators, otherwise future scores will be inaccurate. The example uses 6 blocks with 150 containers needing housekeeping. Initial utilizations are 95%, 78%, 85%, 92%, 68%, and 88%. Iteration 1 evaluates 23 candidate moves and executes moving 8 containers from Block 1 to Block 5 with score 82.4. After 12 moves, utilization improves to 88, 82, 85, 87, 79, and 86%. Operationally, that is a more balanced yard with fewer future bottlenecks. Tier 3 constructs housekeeping move sequences probabilistically. Pheromones encode learned move quality and guide future selections. Better sequences receive stronger reinforcement, and the search converges to lower-cost patterns. Operationally, this method can discover move sequences that a greedy score-based rule would miss. This slide introduces the global pheromone update. Operationally, global updates reinforce the best full sequence found so far, so the colony gradually learns which block-to-block moves tend to reduce cost and improve yard balance. This slide introduces the local pheromone update. Operationally, local updates encourage exploration. They prevent the search from repeatedly selecting the same move too early, which helps avoid premature convergence to a mediocre sequence. This slide introduces move selection probability. Operationally, probability blends learned pheromone with immediate heuristic attractiveness. That allows both exploitation of known good moves and exploration of alternative sequences. This slide shows an ant colony move sequence. Operationally, the sequence matters. Housekeeping is not a single move problem. The order of moves can reduce interference and avoid creating new overloads while fixing old ones. This is the first pseudocode segment for ant colony optimization. Operationally, focus on how a candidate move sequence is built and how feasibility is maintained while constructing that sequence. This segment continues the pseudocode. Operationally, watch how pheromone trails are updated and how costs are evaluated. If cost evaluation ignores disruption or accessibility, the algorithm will optimize the wrong target. This segment completes the pseudocode. Operationally, this is where stopping rules matter. You may stop after a fixed iteration budget or after improvement stalls, depending on how much time the yard has for planning. The reported results use 8 blocks with 200 containers requiring repositioning. The best parameter set is alpha 1.5, beta 1.5, and Joshio 0.15, with average cost 1,198. The best solution found at iteration 67 has total cost 1,198 units, a 15.3% improvement over greedy, and utilization variance drops from 0.082 to 0.031. Operationally, lower variance means the yard is more evenly loaded and less likely to produce avalanche effects. Tier 4 treats housekeeping as sequential decision-making. The agent observes yard state, chooses moves, and receives reward based on utilization, cost, disruption, and accessibility. A deep queue network learns a policy that improves long-term accessibility while controlling near-term cost. Operationally, this is important because many good housekeeping moves look expensive now, but prevent worse disruptions later. This slide defines the state. Operationally, state includes block utilizations, indicators of buried or critical stacks, urgency signals from upcoming retrievals, and possibly forecasts of arrivals and departures. This slide defines the action. Operationally, an action is a housekeeping move choice. Which source block, which destination block, and how many containers subject to feasibility and operational limits. This slide defines the reward. Operationally, reward balances utilization improvement and accessibility against move cost and disruption. If disruption penalties are missing, the policy may move too aggressively and harm service. This is the first implementation segment. Operationally, focus on how the environment simulates yard updates after a move and how invalid actions are excluded. This segment continues the implementation. Operationally, focus on experience storage and sampling. The agent learns from repeated patterns of yard deterioration and recovery. This segment continues the implementation. Operationally, focus on how targets are computed and how the network is updated so that long-term accessibility is valued. This segment completes the implementation. Operationally, focus on evaluation and safeguards. A learned policy must be checked for stability and for not producing extreme churn. This slide shows the deep queue network architecture for the housekeeping agent. Operationally, the architecture must capture both local block conditions and global yard balance, because a move that fixes one block can harm another. Training metrics come from a 10-block simulation over 1,000 episodes. Episode 100 has average reward minus 245.3, epsilon 0.82, moves 28.4, and utilization standard deviation 0.094. Episode 500 has average reward 87.6, epsilon 0.35, moves 19.7, and utilization standard deviation 0.062. Episode 1000 has average reward 156.2, epsilon 0.01, moves 15.3, utilization standard deviation 0.041, and best reward 203.8. The learned agent proactively relocates containers before they become buried. It balances short-term move cost with long-term accessibility benefits. It adapts housekeeping intensity to forecasted demand patterns, and reported performance is 23% better than rule-based systems. Operationally, this is the promise of learning, policies that change with conditions. Tier 5 uses a digital replica of the terminal to orchestrate housekeeping with vessel, gate, and equipment operations. Housekeeping windows are synchronized with vessel schedules to reduce interference. The twin evaluates cascading impacts and selects timing that improves system-wide throughput. This slide presents the integrated digital twin system architecture. Operationally, architecture is about synchronization and interoperability. If yard state, equipment telemetry, and schedule forecasts are not aligned, the twin cannot make reliable coordination decisions. A 350-meter vessel berths at 1,400 with 1,200 import containers and 800 exports to load. The yard also has 150 containers needing urgent housekeeping. From 1,200 to 1,400, the twin schedules a 90-minute housekeeping window with 2 of 6 cranes, repositioning 87 containers and improving critical access by 73% with zero interference. During operations, it moves 23 more during idle periods, then finishes the remaining 40 after departure. Reported benefits versus isolated optimization include 15% reduction in total housekeeping time, 8% improvement in overall terminal productivity, and 12% reduction in equipment operating costs. The scenario also reports zero customer service disruptions, highlighting that coordination can improve performance without harming service. Tier 7 combines human judgment and artificial intelligence into a collaborative decision process. Humans contribute contextual reasoning and stakeholder awareness. Artificial intelligence contributes rapid optimization and pattern recognition. Operationally, this partnership keeps decisions both efficient and practical. This slide focuses on the human and artificial intelligence partnership for housekeeping decisions. Operationally, the goal is not automation at all costs, but consistent, high-quality decisions with transparency and override capability. This slide introduces an explainable output schema. Operationally, explainability means the system can tell you why it recommends a move, what risks exist, and what alternatives are available, so operators can trust and refine the plan. In the example, Tuesday morning at 8:15, 180 containers require housekeeping. A vessel arrives at 1400, and strong winds may start at 1200. The system recommends 142 moves in a 3.5-hour window, from 8:30 to 1200 with confidence 0.82. A human operator reduces the window to 3 hours and excludes premium customer containers in Block 9, producing a revised plan of 127 moves with confidence 0.79. Execution completes 132 moves, wines arrive at 12:15, customer satisfaction is 100%, and cost is $7,950. This practice question asks you to formulate a network flow model for 6 yard blocks with given occupancy and capacity and a symmetric move cost structure. The target is 80% plus or minus 5% utilization, and the goal is minimum housekeeping cost.